So I'm going to get us started here. This is our ChiNamo meetup, and we've not had a Dynamo specific meeting here since Paul stepped down as an organizer. So Ted and I would like to take a couple of minutes to introduce ourselves. My name is Sonia. I'm the person you've been hearing from in the past few months and the co-organizer of our group with Ted. I work as an associate director at BKL Architecture and co-chair with several awesome people, the TAP KC of AA Chicago. We'll be doing some things with them this year, so stay tuned for more announcements. And I'll hand over to Ted for a brief introduction, then we'll dive into our guest presentation.
Thanks, Sonia. Hi, everyone. My name is Ted Hogan, and I'm a senior project designer at JGMA. I am one of the new co-organizers along with Sonia, and I'm also a member of the TAP Knowledge Community of AIA Chicago. I have a lot of interest in emerging technologies and computational design. I have a bit of experience with Dynamo, Grasshopper, and a little Python for both. So I hope that I can bring some of that experience to the group and help everyone up their game a little bit.
Our meeting today is quite special. We're honored to introduce our guest presenter, Durmus Bayryam. If you wave your hand, Durmus. We didn't know Durmus personally and didn't realize until a few weeks before the presentation that he's actually not an English speaker. His emails did fool us. His presentation, which we'll share with you today, has taken us through an unexpected adventure to the cutting edge capabilities of AI and join forces with friends and family. It's been an experience we can have a separate meeting on, but to keep things timely, we'll share with you the work of Durmus, whose article on machine learning in the Dynamo forum prompted this session.
Yeah, what's really neat is that Durmus lives in France, and he sent us a pre-recorded video of his process in his native Turkish, and through the use of multiple different AIs and lots of Googling that starts with the words how to, Sonia and I have managed to translate and then rebuild his voice in English to dub the video for you. So if you have any questions on that process, we can answer all of those today. However, if you have any specific machine learning questions, we'd like you to please put them in the chat, and we'll have Durmus reply to you with a proper translation that we will then circulate via the meetup. And so if you aren't, please make sure that you're subscribed to the meetup platform, as that's going to be our primary way of communicating. With that, and without further ado, will this work? Will it blow up? There's only one way to find out, and we will dive into Durmus's presentation. Thank you all for being here.
All right, here we go.
Hello, everyone. First of all, thank you very much for your kind invitation. I am Durmus Bayryam, and I have been working as a BIM manager at BPA Architecture for 2.5 years. I live in the Montpellier region of France, and today I will talk to you about shapely geometry. So, what does shapely geometry mean for those who don't know? Shapely geometry works together with machine learning. Machine learning is an incredible thing in our industry today, and we can use it directly with Dynamo in our scenarios in Revit. We don't need any effort for this. So how are we going to do this? The key point of the matter is that shapely geometries are actually a Python library. I revisited this about 6 to 7 months ago as a Dynamo version, and now I have made it accessible to everyone as a package within Dynamo. Let's get started if you allow me. I would like to share my screen. Today, I will explain to you how all this works, and then I will explain the logic behind the cluster parking scenario, which means sequentially wrapping and counting parking spaces in Revit. I want to explain this to you because to understand these, we also need to understand the underlying logic. First, we need to know what shapely geometry is, then the models, then the transformations, how the machine learning data works, and how Dynamo geometry integrates within machine learning. First, what is shapely geometry? Shapely geometry includes a geometry package and a machine learning package. The first version only had the geometry part, but today, the second version includes machine learning models, and you can use them. So, shapely geometry begins by manipulating a polygon, dynamo geometry, or any geometry. It can then create, analyze, manipulate again, and present it to you as a data tree or tree list. So how do we use it? We make transformation nodes. Here, actually, a transformation needs to be done because, unfortunately, we can't directly integrate dynamo geometry into ML models. We need to make a transformation between them. We do this with shapely geometry. So how do shapely geometry work? Shapely geometry can first be converted to dynamo geometries and then to NumPy geometries. What machine learning models will we find in the package? These are all of the models used for grouping, classification, and ratio models. So what do all these mean for us, and how will we do these geometry conversions? Here is a very nice example. We start with dynamo geometry, which can be converted into points, polycurves, and polygons, etc. You already know how to do this, but after using conversion nodes, a point, for example, can be converted to shapely geometry. So a polygon can again be converted to shapely geometry and then converted back to a polygon. But when converted, the languages start changing. So actually, as the data changes, the package changes to preserve the data. Here we are looking at a point of dynamo geometry in its shapely version. So we're looking at a polygon, the same data, but only the language has changed. For example, here a polygon comes out as dynamo geometry, but here it turns into a line string format. And a polygon can also be converted to a shapely polygon. But as I said, the versions change, the data is the same, just its name and everything else changes to better fit that package. But as I said, the underlying data is the same in this conversion. No data is lost in the bridge established during the conversion. All shapely geometry obtained here can be converted to NumPy geometries. And again, as I said, no data is lost, just the language of the data changes. So our data is ready, everything is ready, we have created everything. But how will we prepare the model? Dynamo geometry is again converted to shapely geometry, and then to NumPy geometry. And here I will call this label label. Label represents a variable for me. Here I also made a small analysis and said, take all the points within the dynamo geometry, test whether they are inside or outside according to this shapely geometry. If the point is inside, return a true value. If the point is outside, return a false value. In a moment, I will show you a .gif of this example. Before we can understand this better, we need to know how it works. Here I do a list simplification. Here all the NumPy data coming in is appended with the shapely data coming from there. And I call the first variable x and the second one y, and the final variable label. After that, it is exported to a .csv format with a node you can easily find in my shapely package. And now that everything is written to an example CSV file. But let's look at the example. The same input, output, and our variable we used earlier in Dynamo are all here. This is a small-scale CSV file used for training a model. It contains the names of the nodes in Dynamo and their respective inputs and outputs, all organized as our X, Y, and label script. So how can we use this to train a model? If you look, you may notice the formation of this data is actually an autocomplete mechanism. What do I mean? Here comes the CSV file. The CSV file we looked at a little earlier in Dynamo. Its node names representing the inputs and outputs, and also an example node name coming from the into input. So here, If I enter point X, it means that this loop can potentially use all other nodes as a result. For example, if I use the string from object node in my scenario, what other nodes can potentially follow this node in the scenario? The entire logic is like this. If you use this node, potentially, you can continue your scenario with these nodes. Which are they? Other Dynamo nodes can also come to this because this relationship is established. The relationship is entirely based on this logic. If I give a node, for example, here as one, it says that you can obtain a radius using our B point. That is, you need a center point, its diameter, and the output will be a circle. But if this circle node is in your scenario, other geometry nodes must continue in connection with the circle. All this input-output relationship is learned by Dynamo, and at the end of the day, it suggests to us that if you use this node, look, all these nodes related to other Dynamo nodes are also connected. You have a choice of which of these nodes to use. If you know which node to use, you can take it directly and use it. In fact, Dynamo is mentoring the user. This autocomplete came in the new versions of Dynamo, but as you saw, its creation is straightforward. What else can we do, for example? I showed you this transformation earlier. I think it was here. In this transformation, we used shapely contains. I said, I have a polygon. Can you tell me which ones are inside it? Let's see, here we have a rectangle and a circle. Using all these surfaces, I created random points. And here I wanted to show which points are inside and which are outside of this geometry. Blue points represent the ones outside the geometry. Red points represent the ones inside. But as you can see, there are some blue points here. But if we expand the training data of the model, we will see that these blue points slowly disappear. There will be a disappearance here. Look, there's a variable here. This has changed, but if we expand the model a bit more, we will see these blues disappear again. What does this mean for us? This means that the model needs a lot of data for training. I showed you a Dynamo ESV earlier. I also told you that it had very little data. Remember, the more data you use to train a model, the better. And this number should be a minimum of 10,000, i.e. you feed 10,000 pieces of data into the ML model, which is your data set. Then the model starts to produce stable results. For example, I have a typology lodging here, which we are currently actively using in our office. But what are we doing with it? We can automatically draw a floor plan. Let's look at it together. What do I need first? First, I need a line. This is a regular line. Let me erase this. And let's together create a new line. This line has no specific characteristics. This is a random line I drew, and I select this line, and before running the node, this line now represents the corridor length of the building. We can even say it represents the length of the building because it creates itself. And now I said run and used it in the background and produced a floor plan. But a lot of colors appeared on my Dynamo screen. What do they represent? First, this white area represents the length of the corridor. These empty spaces represent circulation areas, and we will move on to examples later. Let me quickly show you how much data a model consists of and how complicated it is. I'm coming back here to return it to its original state. What do these colors represent for us? Let's see, I determined these colors myself as a user because we are currently using these data in our office. This color scale. T1, T2, T3, T4, and T5. These represent the typology used in French regulations for apartments. For example, T1 represents a studio apartment here. T2 represents a 1+1 lodging typology, i.e. apartment typology. T5, T4, T3 also represent 4+1, 3+1, 2+1 housing typologies. Of course, we can change these colors, but right now it showed me an example plan on the screen. But if I change this point, or sorry, shorten its size, will it adapt itself accordingly? Okay, but I want to enlarge this a bit more. For instance, I want to enlarge it this much. Right now, it said that for a building of this size, you need 4 circulation centers, which of course consist of elevators and stairs. And it says it will give you a residential typology in this way. Let's give a floor plan, but what if we mix this up? For example, I'm not satisfied with this typology, and I want to mix it. Let's mix it up a bit more. So here we actually see how easily a floor plan can be created. But what are all these colors based on? As I showed you earlier, they are based on the typology of the lodge. That is, it is based on the data set. As I said, the stronger your data set, the more stable the results you get. Okay, my data set is strong, my geometry is ready, my scenario is very good, but how can I choose the right machine learning model? The answer is critical because, as I said, your data might be complete. Your data set might be complete. Your scenario might be perfect. But if you can't choose the right ML model, everything goes to waste, or you won't get the results you want. Let's see, we have a facade model here and in front of it. There's a wall model. I have a result obtained using the same facade model. I said, look, this is red, and this is red, but I don't want such a thing. What I want is a stable result, a result that continues from here to there, and now I can provide this with KNN. Actually, the issue is exactly that. Both produce the same result, but with different algorithms. Both use the same data set, but the result is different, and that's exactly where the matter starts. As I said, to choose the right model, you first need to know machine learning models. If you know machine learning models, or you don't need to know or read for this, you can use ChatGPT today. You describe your scenario, what you want to do, and you say something you expect, and you ask it to give a recommendation. Okay, let's create a smaller scale housing option together. For example, here we have a typology lodge. Okay, what does this typology lodge provide for us? The scenario is very simple. Here what I need to do is delete this. All I need to do is draw a wall. Of course, this became a very large model. This represents an apartment for me. I put a square meter in the middle of the apartment. I put a room, and using this room, I give the surface value, that is, how many meters it is, to the machine. Then I wanted to predict how many of these it is, like I said earlier, T1, T2, T3, T4. I wanted to guess which one it is, of course, this CSV file. In fact, I had defined it in my office. Let's change that. I'm saying yes. Now it says it gave me a color and came here to typology T5. But if I change this, let's see how the model adapts. For me, it is still T5, so T5, let's reduce it a bit. We drew a very large model. Let's reduce it a bit more. Now its color changed. Okay, what happened? This became T2 for me. Okay, let's enlarge it again together. The color changed again. This became T4 for me. So actually it says, if you make a residence in this square meter, its square meter will be T4. Okay, but I reduced it a little bit. Now it became T3. It said you can only make a T3 in this square meter. Okay, let's expand it. It said, now this is a T5 for you. Okay, let's make it the smallest. I'm changing it again. Now you can make a T1, it says. Actually, machine learning is there to make our lives easier. As I said, just prepare your data and connect it to the model. It's that simple. Right now, all these scenarios are saving us hours in our office. How does it do this? I showed you earlier in AutoPlan, I draw a line, and it automatically adjusts everything to the square meter. Right now, we can only do this within a floor plan, but how will it relate to the upper floors, or from the lower to the upper floor? If you use the T3 in a floor plan here, you use either T3 or T2 on the upper or lower floor. But whether T4 or T5 will come, ML now makes that decision. As I said, the stronger your data set, the more stable and accurate the data and results you will get at the end of the day. We are using these in our office right now. But what I wanted to tell you today is cluster parking. This is a really effective scenario, but the working principle is very simple. So what does it do? You can see a lot of things in the videos you watch today on the LinkedIn account in the videos you watch. So what does this cluster parking do for us? I'll tell you about it if I can find where it was. Is my LinkedIn account open? Not here. Great, no problem. Let's continue from there. Let's see together how I started, how we did it. Here I'm deleting this. Here we have a parking lot. But when we do this parking with classic methods, we do it like this. I also do this. I was bored before. There was a reason I was bored. You create a spine. I will start the sequence from here, and the direction of the sequence will continue from here, then go down again, and then here actually, if you look at it, it represents my direction completely. Okay, we can do this in a residential project, or a competition project, or a small-scale project, no problem. But how will you do this in a large-scale project? If your project is a large-scale project, how will you do this? There is a way to do this with machine learning. I shared it on my LinkedIn account, but unfortunately, I can't access its video and LinkedIn account right now. You can check on LinkedIn. I will go into the details. I will do the details with you. I am closing this. Here we are looking at all the points in a parking within a floor plan. Let me move myself here. Now we are looking at all the points. So what do these points represent? It takes the central points of the parking spaces, and I print them in red here. To make it look nicer, I put this on top like this. Then all this Dynamo data, I list all of it here within itself, and then I convert it into shapely geometry. It will take a bit long to convert into shapely geometry because there is a lot of data. Then I convert all the obtained data into NumPy geometry. Here I also convert it into CSV format. Then all the obtained NumPy data, right now it gave us XYZ, and it printed its floor plan. Then create a CSV file here. For example, I created a file called parking here, but I'm deleting it. Let's create it together with you. So you also see it. I'm just changing its name. I don't need to look at the data inside at all. From there, I find the parking file I created earlier. If I can find it, I found it here. I need to change its name as CSV. I apologize. Yes, then I select the parking file from here. I close this and then come down. This node will come in a future version. What does this node mean for us? Let's go inside and see. This node is a regression model. Here you put a test data. I'm talking about the model inside the .csv file we looked at together. Here it takes everything except the label value. That is, it takes x, y, z, and keeps the other floor plans in y-test. So it takes the x, y, and z data of the point and the label variable data and learns according to this. Using the radius parameter provided by the user, it sorts all these within itself. If the A data mentioned in the X, Y, Z data is here, it enables the user to predict where all the other data are with the B data or the neighbor next to it. This is a bit complicated, but I will show it to you immediately with graphics. Then it starts processing this with the algorithm within the model chosen by a user. And at the end of the day, it offers us a prediction. So what did it do? It's like a serious spider web. I call this network analysis. The model says the first input was here, even saying it has about 9 neighbors. If I come to the second, if this is the second data, the second one has about 11 neighbors. If it's 2, it has about 12 neighbors. So 12 arms are reaching out. Let's look at the details together. What do we mean? As I said, I had mentioned that the first data has about 1, 2, 3, 4, 5, 6, 7, 8, 9 neighbors. Now coming to the second one, if this is the second data, it has about 11 neighbors. If it's 2, then it has about 12 neighbors. I'm entering this, making this 1. It communicates like this, 2 communicates like this. Let's enter a random number here, say 20, and it communicates like this. So actually this point finds its neighboring points and also finds their potentials. It sorts them within itself. But how does it sort? How does it find which is the first, or which is close, or which is far? Or how it will continue after reaching this point? Let's look. If this is approximately 20, this should be the 17th data. Yes, I was right. This data will either continue from below or above, because it comes to sorting from here, finishing the sequence sequentially 1, 2, 3. Then it goes down, but after going down, it has 2 paths. Either it will come here or go here. So how does it decide? If there are 2 points, I can draw a line between them, and I just did that. What do these lines' lengths tell me? Can I look at their lengths? Of course I can. Right now it says 250 centimeters, 250 centimeters, 50 centimeters. The reason it says that is, if we're talking about the first data, even now, let me rotate the point to make it clearer. Let's make it 1 so we all see better. Because 2 points will come for this point. I'm talking about this point. This point has the same length with this and this one, because they are side by side. The first list said 250 centimeters, and again, 250 centimeters for the first list. Then the second coming point, that point, it indicates that it is 500 centimeters away, which is twice the distance. Then it goes up to 1,000, and I can see all its relationships with the lower points here. But we found 250 centimeter values for the points, so actually it's not possible for me to rank them, because it's not possible for me to know which is the first or second. Actually, we can transform all these distance units of the points into another data. You can think of it like attaching weight. I just mentioned that it was 250 symmetry, and I saw two were equal. But are they actually equal, or is Dynamo playing a game? I'm looking at the same model for the 250 centimeter value, the coefficient value it gives here. Here for 500 centimeters, and I find all the other data here. However, when I look at the values given for 250 centimeters, I cannot find the same data because Dynamo rounds them up to a higher number. So actually, I cannot make a prediction using the distances of the points, because when I want to do it, I can find two of the same variables. Whereas when you look at the coefficients, the front coefficients are completely the same, but I can see the difference between them here. You can see how small it is, right? So using all this data, Dynamo tells me that at the end of the day, it gives me a list like this, and your neighbor relationships are like this. You can see how it is arranged within itself on the LinkedIn profile, but the logic behind it is entirely like this. So what happens if I change the radius value? I'm reducing the value, and it gave me a model like this. So what does this model represent? This point will either go right or down. If it comes down, it will either go up or right. Let's look at the x1 point again. Here for the x1 point, it said I will either go right or left. Here we had a model going up. Yes, right now, one of them will either go up or down. But if the sequence continues like this, there is no chance of going up. So it's forced to follow this right direction. So our model drew a diagram like this. But did you notice the relationship between groups is lost? Because a little while ago, I could easily see the relationship between groups because the model was finding a network within itself. It was saying, I will either go up or right or left. It was making this decision according to its own weight model. So how will it make a ranking with this value? If my starting point is here, it will start from here and continue downwards. But which direction will it continue? If this ends with 20, where will 21 be? It could be here. Actually, what I mean is, while doing all this grouping, that is, when using the model, your data set and scenario may be great, but the result you get may not be stable. But if you change the parameter a little more, you can get the result you want. So actually, you need to be very careful while working. That's why, for example, if I make this 200 or 300, let's make it 300. Right now it says I can only move right and left. So actually, if this ends with 10 or 9, if this point ends with 9, the 10th point could be this one or this one or this one. There's every possibility. So we need to see the relationship between them. What if we make this 800? Yes, right now it established its cross connections, but still, we can't see their relationship with each other. That's why, if I set this parameter to 1000, I can see the entire network. To summarize all this, you can use your data very easily with machine learning. Actually, all you need to do is create the right data set, prepare the right scenario, and choose a good machine learning model. If you do these, as a result, your scenario will give a correct and stable result as you expect. You can even use this data set in other scenarios, like I showed you earlier in typology lodging. I'm talking about automatically drawing a floor plan. The same data set and the same data, but the scenario changes, and it gives stable results in both. Thank you for listening to me.
Thank you, Durmus. That was really cool. And I know we had a lot of people that joined a little late. So if you missed it or were not aware, Durmus is not he's not super fluent in English. So what you just saw was actually an AI dubbing translation of his original presentation, which I think was really cool. And I think it showed both how good the AI transcriptions and dubbing can be, and also how confused it can get by certain things that can be a little bit more technical than just how are you doing today. So I think with that, we can open it up to any questions. If you have questions for Durmus about the machine learning presented, please type those into the chat, and we'll send out replies to those once everything gets translated. If you have questions for Sonia and myself about the process of taking that video and kind of translating it to English, we can answer those live. Well, while people think of their questions, I'll say this. So I think that was my first chance to see Sonia's final edit of the video, where she kind of lined up all of the audio with the visuals of what Durmus was doing on screen, which I had seen the audio kind of, and things were not 100% aligned. And, I'll admit, Sonia kept pushing for things to be aligned. And I thought, that's a lot of effort. I don't think we're going to get much out of it. And I stand corrected. I'm learning today how much our language is also what we're seeing when things are spoken, because it really put it over the top for me. I thought things made a lot more sense, and I was watching it going like, I don't remember him saying this before. Like, this makes so much more sense this time. So yeah.
So absolutely.
Yeah.
Yeah, no, we learned a lot from just putting it together. So thank you again, Durmus, and for all of you who joined us. I hope we didn't lose you, but yeah, if you have questions, I mean, I think you're all on the Meetup platform. If you think of something later, feel free to send us your question. You can message us directly, I think, there, or you can put it on the forum. But otherwise, yeah.
Durmus, I know you were saying, go ahead.
Thank you so much.
Yeah. I know you have more examples on your LinkedIn profile. Do you want us to send out a link to your LinkedIn profile via Meetup and people can check it out?
Yes, sure.
Okay.
All right, great. Thanks for the message. I think we're really glad to just have all of you join us again, and we'll look forward to more of these in the future. So
yeah. And if you have any topics you want to request, or someone that wants to present, or anything like that, please feel free to reach out to us via the Meetup platform.
awesome. Have a good day, everyone.
Thanks, everyone.
Bye.
Bye.